Hello, my name is Sulabh Malla, and today I'll be presenting our work titled Coordinated Priority Aware Charging of Distributed Batteries and Oversubscribed Data Centers. In this work, we tackle the problem due to power spikes caused by recharging of batteries, especially in oversubscribed data centers. This figure shows a typical data center power hierarchy where the power from the utility goes to the servers in the racks through a series of circuit breakers. In the case of Facebook data center, the top level circuit breaker is the main switchboard or MSB, which powers switchboard or SB, which in turn powers reactive power panel or RPPs. An RPP powers an entire row of rack, and inside a rack there are power supply units or PSUs, which convert input AC power to DC power, which are used by the servers. They also have battery backup units or BBUs to be used during AC power failures. Data centers employ batteries to power servers during open transitions. Open transition refers to the transfer of power from one source to another. This can happen during utility failures or during maintenances. For example, MSB is generally normally powered by through the utility power. However, in case the utility fails, the backup generator picks up the load, and this can take 10 to 20 seconds. Hence, there is a transfer of power from utility to generator power during utility failure. Similarly, during maintenances, the MSB is replaced by a reserve MSB, and during that transition the racks within the circuit breaker lose power for a brief period of time. Batteries are used during such open transitions. Such open transitions can happen at different levels at the power hierarchy and are frequent in large-scale data centers. The problem is that after an open transition, when the AC input power is back, all the batteries start recharging at the same time, and this can create a sudden spike in the power hierarchy. It can be up to 25% of the server power utilization and can last for over 30 minutes. In case the power spike is greater than the power limit of the circuit breaker, we can have power overloads, and a 30% power overload for more than 30 seconds can trip circuit breakers. A potential solution to this problem is to statically allocate for the battery charging spike in the power budget of the circuit breaker. However, this is wasteful of expensive data center power capacity. Another solution is to cap servers to avoid power overloads, for example, as done by Dynamo. Dynamo is Facebook's data center power management system, which caps servers to avoid power overloads. However, server power capping can degrade performance. This problem is even worse in oversubscribed data centers, as the power utilization are generally high in oversubscribed data centers. Let's look at a real-world scenario. Last year in August, there was a thunderstorm in one of Facebook data center region, and there was a brief utility power outage. After the utility power was back, all of the BBUs in the region started recharging, creating a sudden power spike of about 9.3 megawatts, which lasted for about 25 minutes. This caused multiple server power capping at multiple circuit breakers. To understand why we have power spikes during battery recharging, we need to understand how batteries are recharged. BBUs are lithium-ion batteries which are charged in two phases, the constant current phase and the constant voltage phase. For example, the figure on the left shows charging of battery after a full discharge. Initially, the battery is charged using a constant current, 5 amperes in this case, until the voltage reaches a certain threshold, 52 volts in this example. After that, the battery is charged in a constant voltage phase, whereby the charging current decays until the battery is fully charged. If we look at the power profile of this, it would look something as shown in the graph on right. The constant current phase has almost constant power, while the power decays in the constant voltage phase until the battery is fully charged. If the depth of discharge of the battery is decreased, the time to recharge the battery also decreases, and we see that the decrease is mainly due to shortening of the constant current phase of the charging process. Further, we can note that the initial power, no matter the depth of discharge of the battery, is the same, which results into the power spikes. To solve this problem, we propose a new variable battery charger, whereby we choose a charging current based upon depth of discharge. First, we experimented with different charging currents and measured the charging time for different charging currents and depth of discharge. We found that the charging time increases as we decrease the charging current or increase the battery depth of discharge. We come up with a formula to select the initial charging current based upon depth of discharge, such that we charge the battery within a constant time. In our case, we choose 45 minutes. This formula can be represented as a graph as shown on the right, where we have 5 ampere recharge current at 100% discharge, and it decreases as the depth of discharge of the battery decreases. We also introduced a manual override feature in the variable battery charger, whereby we can manually set the charging current between 1 ampere and 5 ampere. The variable charger is able to lower the power spike compared to the original charger. However, it has some limitations. Since the charging current is selected locally looking at the depth of discharge, we can still have power overloads because it does not take into consideration the available power at a circuit breaker. The available power is defined as the difference between the power limit of the circuit breaker and the server power consumption. Furthermore, the variable charger does not know the priority of services running on the racks. To overcome these limitations, we propose a new coordinated priority aware battery charging, whereby we take power availability at circuit breakers into account, as well as priority of services running on those racks. We first studied the reliability of racks based upon battery charging times. We use the availability of redundancy or AOR metric to quantify reliability, which is defined as the fraction of time the battery is fully charged. We can consider the data center power hierarchy as a series of components, and the input power to the rack will fail if any one of these components fails. We studied the historical maintenance and outage data of Facebook data centers for the past 2 years and calculated the mean time between failures and mean time to repair for those components under different failure scenarios. Using this data, we performed Monte Carlo simulation and calculated the AOR metric as we vary battery charging times. We found that as battery charging time increases, the AOR or reliability decreases linearly. We classify the racks into 3 priorities, P1, P2 and P3, where P1 is the highest priority, and associate a target AOR metric for them, which gives us the charging time SLA. For example, the charging time SLA for P2 rack is 60 minutes, which means that if we are able to charge P2 racks within 60 minutes, we would achieve an expected AOR of 99.9%. Using this, we come up with charging current with a charging current formula for each of the rack priority based upon depth of discharge. We architect this solution inside Dynamo. Dynamo has 2 parts, agent and controllers. Agent is a program running on top of rack switch, which can read and write charging currents in the rack, and this algorithm is built into the controller, which monitors the dynamo agents and can issue override commands to write the charging current for those racks. This highest priority lowest discharge first battery charging algorithm takes input the available power at circuit breaker, the depth of discharge of the battery, and priority of racks, and it outputs the charging current for those racks. It initializes the SLA. Initially, the SLA charging current for all the racks is calculated based upon depth of discharge and rack priority. After that, as long as there is available power, we try to satisfy the SLA of the racks in the highest priority lowest discharge first order. The highest priority first order ensures that a rack with high priorities SLA is met before that of lower priority, while the lowest discharge first order ensures that within the same priority group the number of racks whose SLA are met is maximized. We built a prototype in a Facebook data center and experimented on a row with 17 racks. We conducted an experiment during a planned maintenance where there was an open transition for 5 seconds. After the open transition, all the racks charged at 2 ampere current due to the variable charger. However, Dynamo calculated the SLA charging currents for the racks, and P1 racks were charged at 2 amperes while P2 and P3 racks were charged at 1 ampere, and their charging time SLAs were met. This kind of experiment, especially in a large scale data center, cannot be easily replicated for different scenarios. So we did simulation experiment. For example, in this particular experiment, we simulate an open transition for an MSP with 316 racks, and we compared the original, variable, and priority aware charging. In this particular case, we have 70% battery discharge, and we varied the limit between 2.5 megawatt and 2.3 megawatt. We can see that the variable charger has a lower spike than the original charger. However, when the power limit is 2.3 megawatts, we can still have a power overload leading to power capping. On the other hand, the priority aware charging would proactively decrease the battery charging current and avoid any power capping. Hence, our algorithm minimizes server power capping. Similarly, we compare our priority aware charging with global charging algorithm, where all the racks are charged at the same rate. We decrease the power limit from 2.6 megawatts to 2.2 megawatts. We can see that our priority aware charging algorithm would first penalize P3 racks and then P2 racks, followed by P1 racks as the power limit is decreased, while the global charging algorithm would penalize P1 racks first. This is because P1 racks have higher charging current requirements, while the global charging algorithm charges all racks at the same rate. Hence, our algorithm maximizes the number of high priority racks whose SLAs are met. In summary, coordinated battery charging minimizes server power capping events in data centers. Priority aware battery charging maximizes the number of high priority racks whose SLA are met. And with our coordinated priority aware battery charging algorithm, static allocation up to 25% of data center power capacity is avoided, which would have been wasteful. Thank you for watching. Please refer to our paper for further details and contact me if you have any questions.